Ignition sequence start.
Good morning. Here's a look at the International Space Station Flight Control Room at NASA's Johnson Space Center in Houston and the members of the Orbit 2 team of flight controllers who are monitoring the station's systems and working with the Expedition 65 crew members in the last few hours of their workday. But the work week isn't over yet. Commander Aki Hoshide and his American, Russian, and French crewmates completed one spacewalk out of the U.S. segment of the station this week and are getting ready for another to continue installing new solar arrays on the station's truss structure.
Houston Station on Space to Ground.
Welcome to Space to Ground. I'm Shaniqua Vereen, and it's another busy week aboard the International Space Station, a spacewalk, and innovative science. On Wednesday, June 16th, ESA astronaut Thomas Pesquet and NASA astronaut Shane Kimbrough went out of the Quest airlock for a 7-hour, 15-minute spacewalk. The two astronauts successfully removed the first of the new IROSA solar arrays from its flight support equipment and installed it on its mounting bracket at the 2B power channel on the station's P6 truss structure. Before the new array can be deployed and begin providing power to the orbiting laboratory, spacewalkers will need to install the electrical cables and drive the final two bolts to enable the solar array to unfurl into its fully deployed position on a future spacewalk. For updates on the next spacewalk, follow us on the agency's website and the NASA app. Back inside, the crew kept busy with science, including the deployment of several CubeSats. One of the CubeSats, Ramsat, was developed by Robertsville Middle School in Oak Ridge, Tennessee, is on a mission to study forest regrowth in the Gatlinburg area following the 2016 wildfires and recent wildfires in California. This satellite will use small cameras to capture pictures of growing forests and radio communication to send those images to ground control in Robertsville Middle School's STEM classroom. Ramsat's mission, which could last up to 18 months, began on Monday when it deployed from the space station into its own orbit.
Space to Ground.
Also deployed this week was the Satellite for Orbital Aerodynamic Research, or SOAR. SOAR will study technologies to enable satellites to operate in very low Earth orbit. Such satellites could be smaller, lighter, and less expensive to launch. And that's Space to Ground for this week. Thank you for watching. We'll see you next time.
The next spacewalk that Kimbrough and Pesquet do will begin in the same way all other International Space Station spacewalks do, with the lengthy process of getting into the spacesuits that support the astronauts as they float in the vacuum of space. Want to see what that looks like? Well, here's an accelerated view of the process in which European Space Agency astronaut Luca Parmitano helped NASA's Drew Morgan and Christina Cook get ready for one of their spacewalks on Expedition 61. The International Space Station is the site of science in many different disciplines, from investigators who are trying to take advantage of the weightless environment to gain new insights. For example, the station is home to equipment that could help answer some big questions in modern physics. The Cold Atom Lab facility produces clouds of atoms that are 10 billion times colder than deep space. And thanks to the microgravity environment on the space station, we can observe these atoms for much longer than we can on the ground. Physics is one kind of science being done on the International Space Station. Biology research is another, and the MVP, the Multi-Use Variable Gravity Platform, is designed for research involving many different kinds of organisms and cell types. It's especially important for fruit fly research, as it will allow researchers to study larger sample sizes than before and support fly colonies for multiple generations.
We're looking to answer the question, what is the effect of spaceflight on the host here being the fruit fly or Drosophila, and also on a pathogen. So the bacteria actually is one that can infect the fly very similarly to the way it would infect, for example, a human or any other organism. The genetic makeup of the fruit fly is actually very similar to humans. If you took the human genome and you looked at all the genes that you know are important for function, in that category, in that library of genes, there's 75% similarity between the human genes and the fruit fly genes. In a box this size, thousands of flies can be flown and brought back, so that even if you see an important difference that is small, you can get statistically significant data because you get 3,000 flies or 4,000 flies coming back in a box that size. We have a very nice new piece of hardware. The company TechShot, we've been working together with them for the last few years in developing a very capable piece of hardware.
What's so special about the TechShot MVP is really that there are two internal carousels inside the unit, and each one of them can produce anywhere from 0 to 2 Gs. So it'll be the only payload of its kind in the US segment that can do this. The sample modules themselves do transport to and from the station in the cargo vehicles, but the payload itself, the locker, stays on board the station permanently.
We are interested in human exploration. We want to go to Moon, we want to go to Mars, we want to explore the environment outside of low Earth orbit. And to do that, we need the help of these surrogate model organisms, because once we understand the genes and the pathways, then we know what the countermeasures are that we're working towards.
The International Space Station is helping scientists learn more about plants, too. The Plant Gravity Perception Investigation is germinating seeds in microgravity to study the plant's ability to detect gravity and adapt to grow in this environment, which will be necessary on future missions to deep space when crews will need to grow their own food.
Think about the fact that the shape of every plant you've ever seen is the result of gravity sensing. Every plant has gravity sensing cells, and those cells contain dense bodies. They're packed with starch, and when that organ is displaced away from its starting position, those dense starch-filled packets, they fall to the lower wall of the cell. What we don't know is much about what happens after that. And so our experiment is aimed at what's the least amount of gravity that a plant can detect and cause that kind of sedimentation. And the way we're getting at that is to add fractional gravity to plants as they grow and ask the plant, how about that? Can you feel that much? How about, here's a little bit more. We'll turn it up just a little more. Can you feel that? We're growing 120 of these at all different gravity levels on the station. So we have planned a whole series of experiments at fractional gravity levels while we're visualizing the plants as they grow. So we have a cell culture chamber that has 2 rotors, centrifuge rotors, and these sort of stack, they align along the radius of the rotor at different distances. And the amount of gravity experienced by the plant varies depending on how far it is along that rotor arm. Our lowest treatment, I think, is down to about 6 1,000ths of a G, all the way up to 1 G to get a good control for Earth response. Plant shape is critical in breeding programs to determine optimal growth for crop productivity in roots and in shoots. So lots of potential applications, both off the Earth and on the Earth.
A along with hands-on work with science experiments and spacewalks, International Space Station crew members use some of their time for educational events in which they talk about science with students on Earth, discussing their mission and sharing the value of learning about science, technology, engineering, and math. In this demonstration video, Randy Bresnik demonstrates Newton's second law of motion.
Hello everyone, I'm astronaut Randy Bresnik, living and working aboard the International Space Station. Now, on the space station, we live in a microgravity environment. Do you think the laws of physics will hold up? Come on, let's go find out.
The acceleration of an object depends on the net force acting on the object and the mass of the object, or F equals ma.
Surely good show, Sir Isaac.
Here we see that once the force of the thrust is greater than the weight of the vehicle, the rocket begins to accelerate.
All right, we're going to start with something small, something you might have at home. A little stick of chapstick. We'll go ahead and use our force, being our bungee cord here. We'll put it on our bungee, and we'll pull it back. And let it go. And you can see how fast it accelerates because there's very little mass. Next, we'll try a little spaceship. A little more massive, and you can feel that because as you move it, you can feel that the kind of the force, the extra force you have to push with your hand. So we'll put our spaceship on our launcher here, same spot. Notice it's flying a lot slower than that chapstick did. What we've seen is the same amount of force on a smaller, less massive object means the acceleration is faster. Well, this is the biggest and most massive thing we have, so let's see how the acceleration is affected. Pull back the same amount on the force, and here we go. And there you have it, Newton's second law of motion in action. Thanks everybody for exploring a little physics with me today. Now I'm going to send it back to Earth so you can start your experiments. See you again real soon.
In all of the work being done outside and inside the vehicle, the International Space Station is helping us know what it will take to make successful journeys out into the solar system, to Mars and other destinations. Here are a few more examples of how the station is building the missions of the future.
So you want to go to Mars. How does NASA's International Space Station help us extend human presence into deep space? In the future, when astronauts land on Mars, it will be thanks to some important lessons that we learned on the International Space Station. Rewind. 240 miles above the Earth, the International Space Station is where we currently live and work in space. Here's what we've learned so far. First, there's taking care of our astronauts. Prolonged weightlessness can lead to muscle and bone loss, vision changes, balance, and coordination loss. Thanks to the space station, countermeasures are being developed to keep astronauts healthy for long-duration missions. Then there's the equipment. Spacecraft communication, water recycling, air, and power production are all being test-driven on the International Space Station. What we learn about operating and maintaining our gear in the harshness of space will pave the way for future missions into our solar system. And that's how the space station is helping us extend human presence into deep space. For more information, visit this NASA website.
There is one thing that explorers all throughout time have had in common. They're all at the mercy of the weather. And while things like rain, wind, and lightning all factor in, you can't forget about radiation. The astronauts and the systems of their future space vehicles will have to be protected from deep space radiation. And that's why today's scientists are working hard to improve our ability to accurately forecast dangerous space weather.
The space we travel through. Presented by Science at NASA. When seafaring nations began to explore new regions of the world, one of their biggest concerns in making the journey safely was how to cope with weather. They could harness the wind for power. They could rely on the sun and the stars for navigation. They could build sturdy ships. But if a storm rose suddenly, they were at nature's mercy. More than 5 centuries later, our nation is once again on the cusp of exploring new worlds. And once again, one of our concerns about traveling long distances is the weather, space weather. While space is a vacuum, it's not 100% empty. Particles, energy, and magnetic fields travel through the void. Much of these emanate from the sun's corona, as part of a constant outward flow known as the solar wind, which stretches well beyond the orbit of Neptune. There are also high-energy particles or cosmic rays in the mix, which travel vast distances from dying stars or supernovae. Earth's magnetic field and relatively thick atmosphere act as a shield against the most harmful forms of this radiation, but in space, there is no such deterrent. If we want to travel through this space, we need ways to protect our astronauts. These particles can affect our technology, tripping onboard electronics. Dr. Yari Calatavega, space weather scientist at NASA's Goddard Space Flight Center, notes, "We are working hard to forecast when these particles will be at their peak, such as during solar flares or coronal mass ejections. Acute exposure to these solar energetic particles is a serious concern for astronauts and instruments. Therefore, having a better understanding of when to expect solar activity is important for safely sending our astronauts and spacecraft through space. Ironically, such space weather activity can actually protect against another threat to astronauts. The sun's activity can block dangerous cosmic rays coming from other stars, which are constantly present, illustrating the complexity of the system NASA tries to understand and mitigate for our space travelers. Over time, sea captains learned when to sail their ships and when to stay in harbor, based on their accumulated knowledge of the weather. It's more risky to be on the water in the Caribbean during hurricane season, and you'd want to consider avoiding the northeast coast of America during the height of winter. Dr. Calatavega says, "It's very similar to what we're doing today. We're constantly developing and testing new models to predict space weather, and we're constantly seeking new data to refine those models. A host of heliophysics missions observe space from a variety of vantage points, not unlike terrestrial weather sensors, which work in tandem to paint a bigger picture of our space environment." In August 2018, NASA launched the Parker Solar Probe to help us better understand the sun's activity, especially what drives the solar wind and how energetic particles get accelerated. This data could be used to improve models of space weather forecasting, ultimately helping us find new and better ways to shield our spacecraft and protect our astronauts. Whether it was the oceans ancient ships traveled through, or the space we will one day travel through, we know this: keeping a watchful eye on the environment around us is key to ensuring safe passage. For more information about what matters in space, visit science.nasa.gov.
NASA's Artemis program will return Americans to the moon in a few years and help get us ready to go on to Mars. And knowledge of the geology of both locations will be important. Recently, the next to last man on the moon, Apollo astronaut Harrison Schmitt and astronaut Jessica Watkins, met up at the Johnson Space Center's Moon Rock Lab, so those two geologists could discuss how what we learned from Apollo will inform our efforts in Artemis.
Sample of both sides, but I wouldn't bet on it. Okay, I just got a chunk of that side.
They have what I consider one of you talk about kind of what went into your sampling strategy and how you chose which samples to bring back?
The idea was to get as broad a spectrum of new samples as we possibly could, and that turned out pretty well. We did. And in fact, we sampled at least ejecta, melt, what we call melt ejecta from 3 major basins, maybe 4. We sampled fragments that almost certainly came from the deep mantle of the moon. We didn't know that at the time. That's only recently that we figured that out. And that we also then added to our broad knowledge and history of these volcanic eruptions that have occurred on the moon over time. Now, when you go to the moon on the way to Mars, Jessica, that education I think you're going to get on the moon will be very relevant to Mars. But Mars, of course, does not have that micrometeorite impact environment that we have on the moon, because it has a small atmosphere, about 1/100th of that of the Earth, and that filters out the small impact. The main weathering process on the moon are these micrometeorite impacts and solar wind spallation of the surface. Solar wind's made up of high energy particles, so they actually erode the surfaces of rocks as well as change the character of the debris layer on the moon. On Mars, the dominant erosive force is wind.
Yep.
And so if you're used to studying geomorphology here on Earth that involves wind,
you're in good shape. Yeah.
you can learn a lot about what you're going to see on Mars. But all of that comes from studying the moon.
Right.
If we hadn't had the moon, we wouldn't understand this early history of the Earth, or even speculate about what it might be, speculate intelligently anyway, about what it might be.
Most any astronaut who's made a spacewalk has a story to tell about the moment of their first glimpse of the Earth while outside the International Space Station. Many astronauts report feelings of awe and wonder when they get their first look at the entire planet. Here, Mike Fossum talks about what it was like to really devote some time to Earth observation from that perch 250 miles up.
I've taught astronomy to Boy Scouts for most of my adult life, and know the summer stars in particular like the back of my hand. And I've sought out, I've lived in the Mojave Desert for 8 years, and I would go away from the lights there, even as meager as they might be, to lay on top of a car and just swim, in the universe. So I've always loved the night sky and the stars. And so on my very first shuttle flight, both of my shuttle flights, we took some time. I convinced my crew to turn off all the light in the cockpit, let our eyes dark adapt, and just sit there perched in the windows. All of us were in different windows, and you could see, the Milky Way is just stunning. Of course, the lights don't flicker, they're steady, because they're not coming through the dust and coming through the atmosphere. As you really adjust, you start to sense the very subtle colors that are in the stars. A little bit of reddish, a little bit of bluish, blue-white. And that was, really neat for me to see. The space shuttle was incredibly busy, though, and you don't get much time to look out the windows. It was having the downtime, so you work really hard. The Monday through Friday was a blur. Working late, you're living at work, there's always more to do. And then weekends it slows down some, there's some work. You work out, have a video conference with the family, but you do have some time for some projects and for looking out the windows. And I really got into low light photography in particular. The cupola was fairly new. We had some fairly new cameras, the D3 that was good at capturing low light imagery. I was up there during the last space shuttle mission. So STS-135, Atlantis was docked to the space station, and I grabbed Sandy Magnus, a good friend of mine, and she was on that crew, and she had lived on the space station a few years before, but The cupola was new since she was there. All they had was single windows that looked straight down, and there you're just watching the Earth go by at 5 miles a second. You haven't looked out the cupola yet. Come on, come with me. I've got so much to do. No, Sandy, you have got to see this. So we went in there, cranked the shutters open, and we were flying into this astonishing aurora. Aurora australis, the southern lights. This rippling, pulsing river of green that's down below us, and the red that is stretching up to our altitude. It's like, it was just breathtaking. And I had not practiced any low-light photography up to that point, but I knew right then that I had to figure out how to capture this, and so I started working on that. I called the photography experts on the ground and said, okay, what are the settings I used to get started with this? And part of it was experimental. I had to get close and then start trying. I got some pictures actually of Atlantis docked to the space station in the night with a little bit of the green aurora off to the side. And then I got a picture of Atlantis's plasma trail as it came in over the Yucatan headed toward its landing in Florida. And it's just fascinating. The more you look, the more you start to see the stars like you have never seen them before. I'd give a lot to see that view again.
If you want another look at many of the stories you saw today, you can find them on YouTube and Facebook, along with lots of other great features on a variety of NASA topics. Be sure to look around. If you're looking for good conversation about human spaceflight, check out Houston, We Have a Podcast, our weekly show talking to folks involved in all areas of space exploration. Today, Gary Jordan talks with our colleague Dan Hewitt about the evolution of our coverage of human spaceflight missions as they observe episode 200 of The Little Podcast That Could. Go to nasa.gov/podcasts for this week's episode and all the previous episodes. In fact, the full library of all the NASA podcasts are there. They're also on Apple Podcasts, Google Podcasts, and SoundCloud.